Introduce Keshav and Shiva.
Yes, good afternoon, everyone. Welcome all of you for the third session post-lunch. This is a hands-on session on IBM QisKit. It is presented by our very own student, Mr. Keshav Kasliwal and Shivam Birazdar. Keshav is a pre-final year student pursuing his bachelor's in engineering in electronics and communication from RV College of Engineering. He is a researcher at CIRQUIT Quantum Research for about a year, where his area of interests are quantum cryptography. He is an IBM certified associate developer in QisKit and currently interning at ISRO in the field of quantum communication. He has worked on various domains of quantum computing, namely cryptography, annealing, and algorithms. Okay, we welcome you, Keshav, here for today's presentation. Along with Keshav, we have Shivam Birazdar. He is a computer science engineering student. He's a senior researcher at CIRQUIT RVCA. He's working on quantum annealing and optimization algorithm. He's passionate about quantum physics and wish to pursue his career in quantum research. He has also received, he was one of the finalists in IQAAC 2019, and he was a second runner-up at JPMC Code for a Good Event in 2020. So we welcome you both of you for this hands-on session, Keshav and Shivam. And I request Keshav to start the session.
Yes, ma'am. Thanks a lot, ma'am. Thank you. Thank you for the lovely introduction. So I'll go on with what QisKit is and why is it so important and what makes it way better than the rest. So what QisKit is a software development kit provided by IBM Quantum. So they provided this kit in order to develop and manufacture some good amount of quantum circuits that could help their research in a very good way. So these all are open sourced, and as we know, the advantage of open source is to so the contributions of all across people of all across the world, they can contribute and make up to something better. So this is what QisKit is, and the programming language that that will follow over here is in Python. So I hope that you guys are all familiar with what Python is, and just the basics of it would work, because Python is a language in which even if you read it twice or thrice, you understand what was it in actually. So yeah, so coming on to this was a brief introduction about what QisKit is. So in programming languages, what do is if you want to have some have some libraries or have some functions associated with that particular library in a program to be functioning properly. So what do over here is we import QisKit over here, and there are a lot of functions that these are associated with. So there is known as a visualization of in the QisKit library. So what this does is let's say we want to plot the results in a particular histogram or in a graph. So this is what QisKit visualization does. So so what AIR is a QisKit simulation package, and let's say even if we want to run it on a particular backend for a particular simulator, so that is known as a backend that over here. So we take a circuit, we execute it, and then backend runs the circuit. So by default, execute simulates 124 shots of the circuit. What shots means is it runs 124 times to achieve that particular output that we get. Okay, so there are four types, as we saw, there are four different types of simulators that we have. The first is the chasm simulator, second is the state vector, third is the unitary, and the fourth is a pulse simulator. So we need not to delve into each and every simulator as for now. This is entirely for your information. So as I execute the circuits, you'll get to know as in what do these mean actually. So moving on, so I hope that in these few lectures you might have understood what are gates and how is it implemented, what is the significance behind it. So coming on to the first gate, which is a single qubit operation gates. First we'll classify into single qubit and multi-qubit gates. So what single qubit gates are is, let's say we have a X gate, a H gate, and a Z gate. So these two come. These are the basic single qubit gates that we have. However, there are more single qubit gates over here that is left to you in order to explore it more, because these gates serves as a very beautiful purpose over here. Gives us a very good basis for all the other gates to understand. So coming on to what XGate does, right? So
Keshav, here one
yes,
request is there from participant.
yes, ma'am.
They're saying, along with the whatever the command you are executing, side by
Yes, ma'am.
side, can you see show the execution also?
Oh, yes, ma'am. Sure, sure. I'll do that. So I thought that I'll go through it first and then I'll execute it all in the end. So there's no issue. I'll surely execute it once. I'll explain each and every bit of the code over here. So I'll explain it once. Also, when I'll execute it, and I just wanted to give a brief overview over here. So I
Sure.
hope that's fine. Yeah. So yeah, so coming on to what XGate is, let's say we have studied in you also might have studied in these lectures that what XGate does is simply a NOT gate. If we have the initial state as 0, it flips to 1. So let's say I'll come back. So what do we do over here? Let's say we have the XGate, and the main thing that we should know over here is all the states over here are initialized to 0 state over here. So let's say we had the 0 state, we applied an X gate, and then we measured. So that means that the state that we should get is 1, right? Because that is what the X gate does. So now coming back to the code. So I hope this all is clear with you. If you have any doubts, put it on the chat and I'll surely solve it. Now, how do we declare a quantum circuit over here? So as you can see, this is a variable QC. QC is equal to a quantum circuit bracket 1 comma 1. What is a quantum circuit function doing over here, and what is the significance of both 1 comma 1 over here? So what does a quantum circuit function do is create a quantum circuit having a X number of qubit and a Y number of classical bits over here. So I'll add a comment over here as well. So this is quantum circuit X comma Y. So where X is the number of qubits that we have, or the quantum bits, and Y is the classical bits. Y is the number of classical bits that we want to have. So as you can see over here, QC dot X of 0. If you want to add a gate on that particular qubit, so how do we tell in the computer? So there's this function known as QC. QC is a variable right now, right? Because as we have declared, QC is a empty quantum circuit defining having having 1 qubit and 1 classical bit over here. So now what do we do next is we apply X gate over here on the first qubit. So how do we tell that to, how do we communicate it to it, as in I want to have that X gate over the first qubit. So that is what the this function does. So as you can see over here, I'll highlight it. So this is the QC, or the variable, the quantum circuit variable that we have defined. Now this X is the X gate. So X gate, and on which qubit do you want is the 0th qubit or the first qubit that we only the 1 qubit that we have. So as you know that even in common practices, we start the first element from 0th value, right? Even let's say, even if we take an array over here, array, the first position or the first location that we want to refer always starts from 0, 1, 2, 3, and so on. So that is what we follow over here as well. So QC dot X of 0 simply means that we have applied the X gate onto the first qubit of the QC circuit, the variable QC that we have defined. Now we need to measure this, right? We need to have a perfect explanation, perfect result for this. So what do we do next is I'll also even comment it over here, measure of X comma Y. So now what does measure X comma Y do is, let's say we want to measure the 0th qubit onto the 0th classical qubit. So classical bit, sorry, not the classical qubit, my bad. So if you want to measure the 0th qubit onto the 0th classical bit, so how do we communicate it to the library over here? How do we communicate it in the program? So 0 mentions, the first 0 mentions the, however, this could be a list of values over here as well, because this, since there is a 1 qubit over here, so that is why I don't have any option but to, keep it as it is. But let's say we had a list of qubits, we had 2 to 3 qubits, and we needed to measure all of them. So what do we do here is, let's say we have 0, 1, 2. So this, this gives us the list of what all qubits you need to measure, and on what classical, or to onto what classical bits do you want to measure upon. So this is about the measure function. So I'll erase this so that the program could work properly. So this is the measure function that we have over here. So let's say, okay, how do I explain this? So as we know that the state collapses once it's measured, right? So we need to have that perfect result over here for us to, in order to run the simulator, generate a histogram over here. So even if you don't want to measure, there are certain other things that you can do with that particular state. But however, if you want to measure and then generate a histogram out of it, generate I'll show you in the bottom. So we need to have that certain kind of values, right? Because we cannot express the whole data in the form of, let's say, the specific quantum bit that we have. So in order we measure it and then we plot it on a histogram. So I'll let you know how does the plotting thing work. So this is about the measure function. The first variable in the function corresponds to what quantum bits do you want to measure, and after the comma, it does signify on what classical bits do you want to measure it upon. Okay, so this is about the measure function over here. I'll go. Doesn't mean that I'll cover all of the functions that are available in QisKit. What we are doing over here is we'll cover the basics for you. We'll give you a good kick into QisKit. So maybe you could look upon to various documentations that QisKit has provided. That is really very helpful. So that would assure you, that would help you to be better, understand you in a better way. So this is this is to cover the basics over here as well. Now coming back to the qc.draw function, what do we mean by draw and why is it required? So we need to have the representation of the circuit that we have built, right? Because let's say a visual representation is very much needed to, in order to understand what goes into making of this proper quantum circuit. So in order to represent, in order to visualize it, in order to see it, how does the circuit look? So that is where the qc.draw function over here comes. So what I'll do is I'll maybe execute it right now so that it would execute the time I'll finish my explanation. So qc.draw does mean that we need to draw that function, draw this quantum circuit that we have built till now in order to have a proper visualization appeal of that particular circuit. Okay. Now, coming to the backend. Now, what I said, you right, we need something to run upon it. So now, as we saw this, we'll choose a chasm simulator over here. We'll what do we now? What does this statement mean now? Is we want to have a backend in order to run this circuit, right? Because let's say we execute it and then get the results. So in order for that, we need to have a certain kind of a backend over here. So that is what is known as the we'll choose a simulator for it, and we'll store the variable, store into the variable backend, and then what do we do is we need to execute that quantum circuit, that is QC, onto that particular backend. So that is what execute function does. It executes it over here, QC comma backend, and let's say we get that particular result out of it. So that is why the results is nothing but job.result. So what was the result of that particular job is shown by the results variable. Now what do we do next is we want to have a count over here. We know we need to create a count, as in let's say results.get counts over here. So we need to have that certain kind of counts in order to implement that result over here. So that is what the counts is. We have that result, and we should get a number out of it. As in, how many times does this happen? How many times does this occur over here? So that is what the count function does, and then we plot a histogram over here. So that is what it is now. So let's say if I want to, yeah, if it's executed, yes. So I'll maybe, yeah, correct. Now, what if we had removed the MPL function thing over here as well? So it gives a representation properly, but it not a better visualization appealing way, right? Because this was really good looking, as we said, but this is really required for us to, in order to be clear, give a proper clear appeal, as in what does the circuit mean actually. So coming on to what did I say about shorts over here? Let's say as shorts, let's say 500. Okay, it's taking a bit of a time over here. So I'll come back to what shorts was basically. So shorts was something that even if you run the circuit, it came. So shorts, what's the significance of short is, even let's say even if you want to run that circuit 500 times, or let's say 1,000 times, yeah, the result is the same. Oh, I'll have to execute it from the top. I hope it's clear now. Yeah, so as you can see over here, the result is still 1. So even if we do 1,000 short circuit over here, even if we do not 5,000, so even if we do a 500 short simulation over here, the result is still 1. So that is what it is, because there is a particular uncertainty in the results. Let's say I'll come back to the superposition thing. So it may be quite a bit uncertain, as in, let's say even if we decrease the number of shots or increase the number of shots, the result varies. But since this is a very basic operation, that means that we cannot, there is no significant, let's say an error in what could be the number of shots over here. We not call that an error basically, but this let's say we had run the circuit 500 times, so we have a specific set, numerical set of, let's say, 500 answers over here. So we plot that over here. So that doesn't mean, right, even if we execute the circuit 1,000 times, that means we have a different sample set with us, right? So I'll come back. There is the example for the Hadamard gate and the set gate, so that would make it a bit clear. Somebody's saying something, sir. So yeah, so that is what it is now. So I'll come back. So this is an example of, let's say, what happens if we apply 2 X gates over here. So QC dot barrier is just putting a barrier over here. It doesn't mean it doesn't hamper the function. It just, as I said, in order to make it visually appealable. So let's say the barrier just makes a classification for us in order to make a particular comment on it. So as you can see over here, even if we apply 2 X gates, or let's say in classical system, if we had applied 2 NOT gates, the result would be the same as the input, right? So as I told, the inputs are the same, initialized to zero state over here. So as you can see over here, the answer is 0. So you can do that thing over here as well. Even if you execute that thing for 500 times, for 1,000 times, for 2,000 times, the answer would still remain the same, because there is no particular uncertainty, and the sample set would remain the same for all 500 values, or all 1,000 values, or all 500 or 5,000 values, because this is a simple NOT gate function in classical sense. So that is why we don't get an error over here. Now, so is there any doubts still here? I suppose I'll see in the chat or somewhere. Yeah, it's the Q&A. Okay. So I don't think so there are any doubts. If there is, could yeah.
Keshav, here are 1 or 2 questions. Can
Yeah.
you please show the features we need to import to begin with?
Yeah, sure. So what I'll do is I will share this Jupyter notebook in the drive link as well, which was sent yesterday. So at your own pace, you could, see what libraries we have imported in order to, for the better understanding of it. However, if there is a question, so we from QisKit import star over here. So this as if somebody knows about Python, so import star means importing all the particular functionalities that are associated with QisKit over here. So this is some of the libraries that you should definitely import in order for the proper functioning of the program. However, we'll share the code with you so that you could see at your own leisure, and so that that would help you in better understanding of the code. So yeah, ma'am. So this is all the this is all the libraries that we have imported. So QisKit.visualization does is helpful for us for the plotting functioning, and the compiler is needed for other compiling stuff. So yeah, so this is what we need for the program as for now. So it would differ with, but if you import all the libraries, then there is no issue. But there is a very good practice of importing that many files as what you need, because if you see the program, that would be very good in reading it itself, because we'll see that importing what are folders, what are files, what are libraries you have imported, and then on the basis of that you can easily judge it. So but however, it's very easy for us to import all the libraries at one go, so that we don't get an error. With the chances of getting an error are less. So I see a question in the chat as well. So are shorts and counts different? So no, what shorts is we execute that number of times, right? So shorts is something. Let's say we how do I explain this? Let's say we have a gun. Let's say, right? So we shoot a particular target. So that shooting means you iterate over that particular thing. You go over and shoot over it 500 times over here. So what does it means is we have this circuit over here. We run it 500 times, and then we get that particular count. We get that particular output. So that is what is the difference between shots and counts. So shots is something that when you run it, that is the number of times you run. As we know, in a for loop, let's say we run a particular command in the for loop n times, right? Where n could be anything. So over here, that is the same thing as well. What do we do? What is significance behind shots is we run it, and so run it that many times in order to get a proper understanding. So yeah, so this in order, it creates a list of the outputs over here. It creates a a sample set of the outputs, and then we get the counts over here, and then we plot that counts over here. So I hope the doubt was clear. So I don't understand what epochs is, Ashwini, sir, ma'am. So if you could, explain it to me a bit more properly, that would be great. So does anyone else have any doubts, so that I could move on with the HADMAT operation over here? So
There is one more question, right, Keshav? How to decide the quantum gates for computation? There are single qubit gates and multiple qubit gates. Is there any generalized methodology to choose gates to use the computation?
Okay, so I presume the question was, let's say, how do we look? But that does entirely depend upon what result what we want to achieve, right? So let's say if you want to make a circuit that behaves as a NOT gate, then we'll use X. Behaves as an AND gate, so we'll use CCX. There is a multi-qubit gate over here. So that entirely depends upon what operation you want to perform and what you want to achieve from it. So if you could achieve it from single qubit gates, then it's well and good. Otherwise, if you need a multiple qubit gate, then also that works for it. So that is entirely based upon what you want to achieve over here, what exactly you want as a result. So if it requires a multiple qubit gate, you could use a multiple qubit gate, or else if it requires If it's self-sufficient in a single qubit gate, it's fine as well. So yeah, I hope I answered that question. So is there any more questions? Because I can't see in my chat as well. So you'll have to tell me if it's there. Okay, so I presume that there are no questions over here now. So yeah, I'll come back. I'll go to what. Sorry. Now come back to Hadamard gate over here. So as you may have studied, so what Hadamard gate is, it creates a superposition of both 0 and 1 over here. So let's say if we apply a Hadamard gate on the state 0, so we'll get a plus state which is 1 by root 2 times of 0 plus 1. And what if we apply the Hadamard gate on one state? So that gives a 1 by root 2 times of 0 minus 1. So that means, let's say we'll execute this as well. Now, I'll come back. I'll go over here as well. I'll definitely explain the significance of shorts over here. Now, I hope that this is all understood by everyone, that we declared a quantum circuit, one classical bit and one quantum bit. We wanted to operate Hadamard gate on the first qubit, that is 0. We measured it on the 0th quantum bit onto the 0th classical bit. That means the first qubit and the first classical bit. And we gave a command in order to draw it, and we saw the visualization of it. Now, the significance of short over the significance of shorts over here is this default is 124 shorts that we use. As you can see over here, we have they have initially they have default set a default to 1024. Sorry, yeah. So let's say now if the default is 1024, I'll execute for you once again. The answer for both 0 and 1 comes out to be 0.52 and 0.471. There is nothing wrong in, because as you know, if it is in an equal superposition, if a Hadamard gate is applied, the chances of getting 0 and 1 are both 50%. But why don't we get as an exact 50% over here? We get something more or less than 50% for both 0 and 1. So what is the reason over here is, as I told you, this takes the circuit and executes it, and it runs it, and the short, as I said, 1024 times over here. So we have a limited sample space of 1024 tries over here, right? Now, because it could vary, right? A theoretical aspect does say that it's 50%, but the 1024 results that we have doesn't include all of the equal probabilities that we consider. Right. So let's say even if it's execute and measure, there could be a chance that 0 could be measured more times, or there could be a chance that 1 could be measured more times. So that is the reason why the probability of 0 is slightly higher than 1, because in the 1024 sample space that we have created, the number of zeros would be number of zeros measured would be more than the number of ones measured. So in order to give you a particular significance as to why shorts are indeed important, so let's say, look, now the numbers are changed, right? I showed you that it was 5.528 and 0.471 something. Now it's changed to 0.508 and 0.492. Why is it? What happened to it that it changed its count? This is the reason why 0 and 1 is there, because the values are changed, because now we have a sample space of 500 over here. So when we execute it, when we measure it, and then we'll see that the number of zeros are approximately same to what we have for 1. So that is the reason why shorts are indeed important. It gives a particular data, it gives a particular interpretation to the data that we have. So that also affects what you will see as the plot. But however, this wouldn't change the theoretical back that it has. That means if the state is 1 by root 2 times a 0 plus 1, the probability of getting 0 is 50%, and so is for 1. So this is something that, we have a sample space, right? So even if we show this and we measure it, there is a chance that one could be more than zeros because we have a specific sample space that we have. We have this cloud of data that we have. So what decides number of shots? That is entirely dependent upon us, right? But a default, because we take it a default number to be 1024 because while developing, the developers of QisKit found it to be self-sufficient in order to understand that 1024 shots was indeed complete and gave a very good results of it. But this is what shots mean. So let's say even if I run it one time, so let's say we run it one time. So probability of what getting, look, I'm getting an 100% probability of zero. That means that's one sample space that we had, it measured zero. So let's say even if we take two, let's say now it takes zero. But as you increase the number of because this cannot judge, right? This cannot be truly interpreted that Heidenmark gate works in this way. That is wrong because it has a very limited sample space that it has. So let's say we have 10 now. We'll take shots 10 right over here. Now, as you can see, if we executed that circuit 10 times, so we got 0 to be 3, 3 times 0 and 7 times 1. So that is what I meant by restricting a sample space to a particular number. But that is why the developers felt that 1024, or even if I remove this, the default number of shots is 1024. So when I remove this, I'll get that particular optimum result that is required by developers. So that is the reason why that is the significance behind shots. So we execute the circuit n number of times, and then we get the result. We store it, and then we plot it accordingly. So we plot the probability histogram of it as it is. So I hope you guys, you all got the significance of what shots are and why is it indeed important. So I'll check the chat once. Okay, so I don't have any questions as for now. Now, what if it was like minus state, that is 1 by root 2 times of 0 minus 1. So how do we get that? Okay, so there's another question over here. We know from statistics that if the number of shots are increased, the expected probability distribution will be reached. It is true, but there is something known as the computational limit over here as well, right? Because even if I cannot execute a 10,000 short circuit over my laptop because it would hang everything. But that is what I meant. Then your point is absolutely very correct that if we increase the number of shots, then we have a large sample space. Then we have a large set over here, set of numbers that would converge to the exact result that we have. But however, this was optimum. Even if you give it to be 10,000, 1 lakh, and then that would converge to 0.5 and 0.5 as well. That is absolutely the point that I made was absolutely correct because if the sample space go on, the size of the sample space goes on increasing, we have that particular 50% chance the thing on our sample space as well. So as I just showed you, I had taken 10 shots and I got the probability to be 0.3 0.7, right? Now when I did for 1024 times, it automatically converts to 0.497 and 0.503. So as you go on increasing the number of shots, that would truly converge to 0.5 and 0.5 as well. So exact 0.5 and 0.5, but as you know, there is a certain computational limit on the local systems as well. That is why we don't indulge in executing it all. But yeah, if you increase the number of shots, according to common logic, that is true that we'll converge to the perfect 0.5, 0.5 answers over here. So that is what it is. So even let's say I'll increase the shots to 5,000, let's say. Okay. Look, 0.501 and 0.499. So is the answer converging to a perfect 0.5, 0.5, right? So even if you increase the number of shots to 10,000, 50,000, 1 lakh, you'll converge to the proper and optimum result that we have, that is 0.5 and 0.5. So this is the, as you said, this is the beauty of statistics, right? Because And that is what I wanted to infer from here as well. We cannot entirely depend upon statistics to show what is the property of that gate, right? Because according to, let's say, even if no one knew about the Hadamard gate and he saw the results, so he would say, right, even let's say the shots was 10. So he would say, right, that the probability of occurrence is 0.3 and the probability of occurrence is 0.7, which is not true for an Hadamard gate because the probabilities are for 0.5 and 0.5. So that is entirely dependent upon the sample set that we had, that the sample space that we have generated. So yeah, I hope I answered your question, sir. So yeah, if there is any more questions, please do let me know, because this is indeed a very interesting point over here to make, because the number of shots does decide the statistical result of it, but not the property of the circuit over here. So that is what I wanted to, mention over here. The statistical property is truly dependent upon how many times you run that particular circuit, but it doesn't, it doesn't show the proper property of it, the property of that particular gate. It is may or may not be true, as in common terms. So yeah, so this was the significance of the shots over here. I'll go on to look. It may not be necessary that for the same number of shots you'll get the same result, because let's say now what does the computer do? What does the simulator do is it would take that circuit again, it would run it 5,000 times, and it would generate a result. So that wouldn't mean that the answers, the results that you got for the same shots for the first try wouldn't be same for the second try. So this intrinsic randomness of quantum computing, quantum mechanics does entirely benefit us, because as more the randomness of the data, more it would be secure to any means, right? That's a different topic, but as you know, the randomness does give a very good explanation for security purposes as well. So this is the randomness of these quantum systems to give a particular good output of it. Now the probability graph was the minus state, that is 1 by root 2 times 0 minus 1, is the same, because even if there's a negative sign over here, I'll show you the state over here as well. Yeah, it's here. Even if there is a negative sign over here, the probability would still be the square of the mod, right? So the mod converts into the plus, and then this would be, as I this would will get this as an output over here. So the scheme is same over here as well. So there is nothing different over here. Now, coming back to a very interesting property of such gates is reversibility. Now, what that means is, even if you apply those gates 2 times, even number of times, that would result into the same initial state that you have given. Now, let's say we have the initial state to be x, right? Sorry, initial state to be 1 state over here, but after applying a x gate, that means all the initialized to 1, 0, and then after applying a x gate, you got the state as 1. Now we have applied a Hadamard gate, and again applied a Hadamard gate over here as well, and then we measure. So what that means is, what I said was about reversibility. Now, according to what I said, the answer should be 1, right? So because this was the initial state for both the Hadamard gates over here, that means the state 1, because 0 was operated an X gate on it, and then we got the 1 state over here. So let's say I'll execute this as well to create a proper flow. Yeah. So as you saw, we got the state 1 over here. So that is a very interesting property of quantum gates, that is reversibility. So that means you get back the exact input that you have. So in classical systems, this is only true for a NOT gate, right? Because if you apply the NOT gate 2 times, you'll get back the exact input. Sorry, from the output, you'll get back the exact input. But this is for quantum gates, this extends the properties to a lot and a good scale. So even if you create the quantum classical equivalent, or say quantum, quantum and gate. That means so that could give you the exact state. So so that would give you the exact state over here. So yeah, there is a question that would I be sharing the content? So yeah, absolutely. So as a drive link was shared, uh, so as I shared as I told you, there was a drive link shared over there on the WhatsApp group. So we'll share all the resources, all the Jupyter notebooks over there for your practice. So that is what we intend to do. So coming on to the Z-gate. So what Z-gate is does the same thing. Z of 0 gives a 0 state, and the Z of 1 state gives a -1 state. Now, yeah, this is nothing to explain much, because this is sorry, who wasn't okay, sorry. Yeah, now it's executed. I'll come back to your question, Nishit, sir, just a moment. Yeah, so I'll explain this and I'll come back for further questions. So what does the Zgate do over here is Zgate is also known as a relative giving a phase gate over here. So phase flip gate, a phase flip. So the X gate is also known as a bit flip, and a Z gate is also known as a phase flip. So what is significance is, if a Z gate is applied on 0 state, that means let's say if we apply the 0 state over here on if we apply the Z gate on the 0 state, we get 0, and if we apply the Z gate on the 1 state, we get to be as 1 or -1. So let's say we need to have conditional a conditional gate over here. Let's say if the state is 0, then it's 0. If the state is 1, reverse the flip. So that is that is very important for us to in order to understand to classify database specifically. If the state is 1, flip it, or flip the phase, sorry, or else if it's 0, then remain as it is. So this is sort of, you could see as a classification technique over here as well. So let's say we have we apply the Z-gate, we get the count. So as you can see, if the Z-gate was applied on the 0 state, so however the probabilities doesn't get affected by the phase, right? Because all the probabilities are calculated by the mod of the square of the mods, right? So the negative is converted into the positive, and then we continue with it further. So that is what what we meant by the Z-gate over here as well. So I'll come back to the question. So what is the significance of barrier? So yes, sir. So the significance of barrier over here is nothing. It doesn't affect the this basic functioning of the circuit. It is just for us to classify it into for a better visual appeal. So even let's say if I had removed the barrier over here, so that means that it would all be accumulated, right? So then I couldn't give you a proper saying as to the initial state was what. So this let's say it creates a classification between this was the initial state and this was the other side of it. That is something different. So in order to classify it properly, in order to visually classify it, we just put a barrier. However, it does not affect the proper functioning of these circuits. It does not affect the results. So it does, but it is just for our proper visual classification over here. So I hope that's clear over here now. Is there any more questions, by the way? So this was about the single qubit gates over here. There are a lot of single qubit gates except from this as well. This was just to give you a brief intro about what it is, how it is how it is going on, and how do we apply these single qubit gates, single qubit operations upon it. So I hope that this was clear. And if you have any doubts, I'll wait for a minute or so. And if ma'am could let me know if there are any questions as well. So yeah, is there any questions, by the way? Meenal ma'am, is there any questions? Or
No, there are no questions, Keshav. You can carry on, I think.
Okay, ma'am. Okay. Thank you, ma'am. I'll go on with the multi-qubit operations now. So what is now coming back to there could be a lot of changes over here now. So what is the difference in the functions, the difference in declaring the functions from a single qubit operation to multi operation does differ. So let's say what is CX gate now? CS gate is simply a C0 gate over here. So C0 C0 stands for a controlled knot. The C stands for control. So what does it mean actually is, let's say I'll first explain the significance of the CX gate. So let's say we have this Q0 over here now. So we the control is this and the target is this. So we'll see this as the control and this as the target. So let's say if the Q0 is 0, if it's initialized to 0 state, that means Q1 wouldn't be affected. But if the Q0 is 1, that means the Q0 operation is applied on Q1. That means the bit would flip. So I'll execute it once. So yeah. Now since these Q0's initial state was 0, the Q1 would okay. So I'll just a minute. Yeah, sorry for the interruption. Okay, so yeah. So sorry for the interruption over here. I am extremely sorry. So I'll go on with the explanation right now. So let's say we have the now. So what do we do over here is we have the Q0 over here. Q0 is known as the control, and Q1 is known as the Q1 is known as the target. As in what does the control effect on the target, right? Now in order in order to justify what I just said, I'll give I'll give the state. Okay, so before that, this, as you can see over here, the state is 0, right? So keep that in mind. Now we initialize the state Q0. Yeah, exactly, ma'am. So I just reversed it to 1 now. So let's say we have now the Q0 is changed to 1. So according to what I just said, the Q1 should also be changed to 1, right? So this would be a perfect explanation to it. As in, if the state Q1 Q0 is 1, is initialized to 1 state, so so that means the Q1 state would be flipped. Now in order to flip, in order to give a proper explanation for all the possibilities, we'll initialize the state Q1 to 1 only. Now according to what I just said, it should apply, the bit should flip, right? So according to that, it flips. So this is what this is what it is for Q0 for the CX gate as well. That means on that control, if the Q0 is set to be that particular control, that means that Q0 does affect the state of Q1, right? Because it has a proper control over it. So that is what it is. Sorry, that is known as the C0 operation on the CX gate over here. So how do we apply these gates? So I gave you a brief over here. Now, as I told you, the first input to the quantum circuit function is the quantum bits, because we need 2 quantum bits over here and 1 for the classical bits. Now I'll comment this as well because this would not be needed. Now, how do we apply a CX gate over here? Is CX, this is the variable that I have declared over here for the quantum circuit. Now, .cx means we apply a CX gate on 0, setting it as a target qubit, and 1 setting it as the, 0 setting it as the control, and for the 1 second qubit, right? Because 0th is the first qubit, and the second is the 1 is the second qubit, right? So that 0, 1 from the control to the target. That is how the format for the CX gate is. So 0 is for the first qubit. It infers that the first qubit is the control, and from that the second qubit is the target qubit over here. So that is what it is now. So now we want to measure, right? We want to have the certain outputs over here. So we measure it and then we draw over here. And the same story over here, we had chosen a backend as we didn't change the backend over here. We chose the backend to be where did I declare it? Yeah, backend is the chasm simulator. So that would help us in creating histograms over here. So there I haven't made any changes as much. So let's say now we the same story again and again. We execute it, we get the results, we generate accounts, and then we plot over here. So this is what it is now. So I hope everybody has understood the various aspects of CXKit. So if there are any questions, do let me know over here. Is there any questions, by the way? So I'll wait. I'll just pause for 30 seconds over here, and then I'll continue to the next topic. So. Okay, so I hope there aren't any questions. If there are, so if you feel, you can automatically put in the chat and I'll answer. So coming back to the CCXKit. So what CCXKit now is, as for the name, you can slightly infer from it that that means that there are two controls over here and the third as the not operation. So that is the exact meaning of it. That means there are two controls, and if both of the controls are one, initialized to one, then and then only the not operation would be applied over here. So that means that let's say we have the C6 gate over here. So what do we do over here is, as you can see from the diagrammatic representation, that there are two qubits, there are two control qubits over here, and there is a third target qubit. Okay, so from this you can infer that if it is, if it would be let's say, how should I explain this? Yeah, so Q0 and Q1 are both controlled. So we can infer it slightly as an AND gate, right? Because if both of the controls are one, then only the Q2 is flipped. So that is slightly a good indication towards the AND gate, right? Because let's say we have two inputs, 0, 0, 0, 1, 1, 0, and 1, 1. So this also does signify that if the two controls aren't one, so aren't one, then the result is always 0. But however, if both of the qubits are 1, then and then only the output would be 1. So that is what we signify from here as well. That is, if both of the qubits are 1, then and then only the state of the Q2 will be flipped. So that is, that is a slight indication towards the classical counterpart. So I'll execute this as well. So same story over here. Because we now need 3 qubits, we initialize the quantum circuit to be 3 qubits over here. So and then a 1 classical bit. Now what do we do over here is, now how do we declare the C6 gate is taking first two inputs as the control and the third as the output. Oh, sorry, the target. Sorry. Yeah. That means 0 and 1 are served to be as the control over here, and the second second 2, that is the third qubit, that is served to be as the target over here. So that is how do we declare a CCX gate onto QisKit. So then what do? We measure the output, that is output on Q2, and then we draw it and then we execute it. So I'll first execute this sample state over here as well. So let's say we have now this is 0, right? Because as I said, it both should be 1. So even if one of these states are 1, that means the output is still 0. I comment this again and I'll uncomment this too. Yeah. So that means over here that, this is still 0. But what if both the qubits are 1? Then what do we get is simply 1. So that is what it is, right? So this is the basic functioning of what CCX gate does. So that is because, as I said, it gives a very good classical counterpart indication to AND gate. So if both of the inputs are 1, then we get 1 as an output, right? So this is, this is could be converted as a classical AND gate too. So yeah, so moving on to Bell state. So I'll, just give me a moment or so. I'll have to confirm from someone. So uh, yeah. So meanwhile, if you have any doubts, please let me know. I'll drink water for a moment. So if you could allow me.
Yeah, meanwhile, one announcement here. Actually, our second speaker for the talk, Shivam Virajda, due to some technical issue, he is not able to join this link. So he will be joining some Google Meet we have created, and we have sent it the link to your mail IDs. And I'm sharing that link here also. So if you're not, if you didn't get the mail, you can join the Google link through whatever the link I have shared just now. Okay, so after Keshav's session, Shivam will be taking session using Google Meet instead of WebEx. Yes, Shivam. Yes, Keshav, you can continue.
Yes, ma'am. Thanks a lot for the indication. So does anyone have any doubts over here till now? So I'll cover this would be the last topic in this Jupyter notebook, that is the Bell state. So till then, because what Bell state is a combination of both a single qubit and a multi-qubit gate. Okay. So with that, does anyone have any doubts till now? Because that in order for us to proceed, the above things are very needed for us to be clear with. So does anyone have any doubts till now? So I'll wait for a minute or so. Till then, if there are no questions, then we'll definitely proceed with it now. Yeah. So I feel there are no questions now. So I'll go on to Bell state now. What Bell state is let's say it creates Bell state has these four possibilities among us in such a way that it gives us the four entangled states. So as you can see over here, these are the four entangled states. Let's say if we give x and y are both 0, 0, we get it as 0, 0 plus 1, 1 divided by root 2. So the purpose of quantum entanglement is there isn't a separate identity for it, right? Because if these are measured, then the other would also collapse. It would have an effect on the second qubit as well. So that is the basic purpose of what entanglement is. If you procure a change, if you put a particular change on it, that would affect the second qubit as well. So coming on to so someone has put in the chat that will share the Jupyter. Yeah, I'll surely share the Jupyter notebook on the drive links as well. So yeah, so going on to what I'll execute this now. Let's say the Bell state. Now coming to the Bell state, what does it do is it gives we apply an execute and then we entangle it over here. Now this third set gives a superposed entangled state over here, right? So let's say we get it to be 0, 0. So 0, 0 plus 1, 1 whole divided by root 2. So that is what we wanted to have, right? If we, if this input state was 0, 0. Now, coming back to what if the state was, 0, 1. So I'll put X gates over here, right? Because that is needed for us to give a proper answer of it. Now, if the X gate, if we apply X gate over the first qubit, that means 0, 1. Now the answer should be okay. Why did it come? Yeah, okay. So I applied the qubit on the we applied the X gate on the first qubit. That means we have 0, 0 minus 1, 1 divided by 2. Now, what if I had applied the X gate on the first state? Well, dot X of 0. Oh, sorry, X of 1. Sorry for that. Now that means we have two X gates. Now the result is 0, 1 and 1, 0. So that means a 50-50% chance of both 0, 0, 1 and 1, 0. So that is what is signified in 1, 1 over here. That means 0, 1 minus 1, 0 whole divided by root 2. So just to point out what is the significance of entanglement over here is let's say we have this state over here, 0. So the first qubit is 0. That means second qubit would be 0 without any interference, without any checking on. We can definitely claim that if the first state is 0, then the other state would exactly be 0 as well. For this, if the first state is 0, the second qubit would exactly be 1. If the first qubit is 1, then the second qubit would definitely be 0. So this is the assurance that quantum entanglement gives. So if the first qubit is 0, then then we could definitely, by seeing the first qubit, we could definitely infer that what could be the state of second qubit as well. So that is the theoretical experience that the theoretical path that quantum entanglement carries. So that you can see over here as well. So yeah, so I won't tell. I'll take another state as well. Let's say I comment this over here. So that would give me 0, 1 and 1, 0 only, but in a different manner. So as you saw, as I told you, the shorts does give does affect the statistical results. So moving on, yeah, this is all about best states that I have. I'll definitely share the Jupyter notebooks with you all on the drive link for you to practice. So before going to the Day2S algorithm, does anyone have any doubts till now? So for the Bernstein-Vazirani algorithm, will move on to the meet link. So till then, I'll cover my algorithm first, and then you could go to the meet link, and then we'll proceed our session from there. So till then, does anyone have any doubts till now? Anyone? So maybe I'll see the chat from this one questions. So if there are any doubts, do let me know. We'll solve it together. And because it's very necessary for you to clear your doubts on the spot, because this is the only time that we could, have a good discussion about it, and your doubts could be cleared in a better manner. So if there is any doubts, do let me know. So yeah, I'll wait for a moment. If anything related to QisKit, anything related to what I just told in this hour or so. So if you have any questions in related to anything, what does this mean? What does this mean and all? So why do we need draw function? Why do we execute? Why do we follow these steps? So if there is any questions related to that, do let me know. This is the perfect time for all of us to clear all of your doubts. So is there any doubts till now? So I'll wait for a minute. I'll wait for 30 seconds or a minute or so. Then we'll continue with the algorithm now. So yeah, so meanwhile, what I'll do is I'll go on to the algorithm now. So yeah, so in all of the notebooks that we'll share, we have this certain kind of functions over here. If no one has installed QisKit, also maybe they could just uncomment these lines, and then you can install it on your own pace, on your own scale now. So moving on to now Day2S algorithms. So since I don't see questions over here, now we'll move on. I'll just give a brief overview first of what you have studied in theoretical aspects as in the last session. Now, what do we do on a Day2S algorithm is we see whether a function is constant or balanced, right? So this would be explanation over here as well. So I think so maybe some bit of the practical experience over here for the DTA algorithm has been covered, but I'll make sure that each and every one of you have understood the explanations over there as well. So the first state, what do we do over here is we create a quantum circuit. Now, how do we create a quantum circuit is we declare a quantum circuit over here, and so the difference between declaring there and declaring over here is we give certain names to it now. So this is entirely not necessary. You can even declare it how we have declared till now. But this is just I said for a proper visual appeal over here. So if we can follow this, that is well and good over here. Now, however, if you don't want to follow, that's up to you, because as I said, this is entirely for the visual appeal. So now coming on to the declaration part of it. This is the quantum register over here, and the number of qubits, the name over here, and then we add the register, and then the register is the data data is the quantum register, and the head register is the classical register. So that means what does it do is we add the quantum bits, we add the classical bits over here, and then we just draw over here. So that is the lines created in it, indicating the number of qubits. And this, as you can see over here, this does represent the number of classical bits that was generated. Okay. Now moving on to the implementation part of it, we create a superposition now. Okay, so sorry I didn't execute it over here. Yeah, I'll wait for it to execute for a moment, and then we could clear over here. Now as we know, we applied all the Hadamard gates over here. Yeah, as you can see, now we get we perform a uniform superposition. That means we apply all the Hadamard gates and all the edge gates over here on all the qubits over here. Sorry. So what do we do next is we create the ancilla qubit. Now, what do we do over here is we just add a ancilla qubit over here, and then we perform an X operation and an H operation over here. Now, once again, this barrier is for, okay, sorry, I executed it again. I'll go on top. If it is fine now. Yes, fine. Now, the barrier does, as I said, just for the classification purposes that we have. That means that this is the entire input state. That is the input state that we have generated. So that is, the main step that we had to cover. Now, the second main step, that is creating the oracle. Now, if we want to have a constant oracle, we don't need to, let's say we don't have to change anything over there, right? Because if there is a constant circuit, we would send it like that itself. So that is what it means. So if the function is function called as a constant oracle function, that means we would return the exact circuit as it is. Now coming back to balanced oracle. Now what do we do over here is we need to have something different over here, right? Because the balanced oracle is the number of ones are equal to number of zeros and so on. So what do we do over here is we have that data qubits onto the ancilla qubits. We perform CX gate operations and all of the data qubits onto the ancilla qubit as the target. Okay, now since this was the balanced oracle circuit that we had called, so that is the main reason that we have CX gates over here. Now, however, now what do we do next is okay, I haven't called. Yeah, I'll call. I'll put another Hadamard gates, a series of Hadamard gates on all the qubits, and then we measure all the qubits over here. So as you can see, the results does signify over what we had learned in the theory as well. So okay, so I have to maybe I'll comment this for the proper understanding. So this is one of the reasons why that is something the dark background function was something extra. So that is what if I had, okay, so okay, I'll leave it till here. So I'll see whether what could we do with so yeah, so never mind. So I'll not go into that. So that means that what results that we had that could give us in the single shot, right? So that we gave over here as well. That means if we execute this circuit over a single shot, that means the result would be consistent that what we have studied, right? So this is all about the Day2S algorithm. So if anyone has any doubts over here, do let me know. I'll wait for a moment, and then afterwards we could proceed into the meet link now. So if there is any questions related to both of the implementations, that is the for the the single qubit and the multi qubit and the cascade or the Day2S algorithm, do let me know. I'll wait for a moment, and then we could all proceed to the meet link. So if there is any questions, I'll wait for a minute or two, and then we are good to go. Yeah, so if there isn't any, if there is any questions, okay. Yes, so I'll wait for questions and then we'll wrap it up now. Okay, so I don't see any questions. However, if you have any doubts, we'll always be available on WhatsApp as well. So thank you. Thanks a lot, everyone. So maybe we'll all proceed into the meet link now. So yeah, thank you, ma'am. So ma'am, could we proceed to the meet link now then? I'll finish with my session.
Thank you, Keshav, for this hands-on session.
Thank you.
And he is a quantum researcher from our circuit team, and they are always conducting this kind of workshop. Again, thank you so much for joining. And our second session, as I told, it will be continued using Google link. So I request all of you to join this Google link as we have shared on mail, as well as in the chat box also I have shared it.
Okay then. So thanks a lot, ma'am. Thank you. Thank you, everyone.
Thank you so much.